All right, good afternoon, everyone. Today's a great day. First, I'd like to announce that two of our grad students just received the GRFP. So go grads. Right. And second, it's my great pleasure to introduce the speaker for today, Roisin Commane. She's coming to us from Columbia University. Dr. Commane, or Professor Commane, received a bachelor degree in chemistry and applied math from Dublin University in Ireland, and then a master's degree in biomolecular science from Imperial College London, after which she went to get a PhD in atmospheric chemistry from the University of Leeds in the UK, and then did a postdoc at Harvard University with Steve Wolfsey. So we're very excited because she works in the Arctic and in urban systems and has lots to share today. Thank you.
Thank you. This feels very high-tech. Sorry, it looks so funny. Thank you very much for the invitation. It's been great chatting with everyone about such cool stuff so far. So I was going to give a very kind of brief overview of some of the stuff we've been doing. I moved to New York in about 2018, and it has gotten me interested in different things as we've gone along. So the graph in the background of this is actually from the GMAO model. It's a simulation of CO2 around the world, and they've got amazing models for what they can represent. But a lot of the time, there's a lot of uncertainty that's driving some of what they're transporting around. So what I'm looking at today is different components of that cycle. So both the urban and then looking at the Arctic. So 2020 and 2016 are tied as the warmest years on record for global temperatures. But that doesn't mean it was warm everywhere. In fact, there's a very big disparity in what kind of numbers you see for warmth in different places. And this is the data from January of this year, 2023. And you're looking at massive warming, and much of it is in the Arctic. Now, the Arctic is the kind of place where in January a 20-degree increase in temperature, it's still cold, but it's not as cold as it used to be. It's not getting as cold as it did during the winter. So much of this warming is driven by greenhouse gases, and by that I mean CO2, methane, nitrous oxide, N2O, and that's most of the kind of volume of greenhouse gases. I'm not going to talk about anything to do with the rest of them, which is like CFCs, ozone, all that. But the warming has an effect on the ecosystems in the Arctic. So the reason we worry about that, most of the Arctic is underlain by very thick layers of carbon locked up in those soils. And if we think if the Arctic used to be acidic, so it took in carbon for an awfully long time. So there's enough carbon locked up in those soils to add about 700 ppm of CO2 to the atmosphere. That's double what we have now, almost. So the potential is there to release huge amounts of carbon. Now, we don't think that's going to happen tomorrow. I'm a bit freaked out about how sooner it might be happening than I thought, based on some discussions today. But we need to learn, how are these soils, how are these ecosystems responding to all the warming that's coming in? And how is it now versus in the future? We can't predict something if we don't understand what's happening now. So some of what I'm interested in is, okay, we can measure things like CO2 in the atmosphere. And this is a long-term record from Mauna Loa. I heard recently that they're back measuring at Mauna Loa after after some incidences with lava all over roads. So we look at this long-term time series, and you can see how much it's increasing over time. So that's the big black line on top. But then you see all these oscillations on top. So you've got the uptake of CO2 in the summertime from all the biosphere. So all the trees take up a huge amount of carbon, the oceans take up carbon. And then we look at that oscillation moving through the years. Now, CO2 has the most impact on climate just because how much of it there is. We're talking parts per million of CO2 in the atmosphere. And these numbers have actually been rocketed up in the time since I've started making these measurements. So I assume many of you have heard about, oh, what was the CO2 number when you were born? It's amazing how much that has changed. And that's one thing that still scares me about all of this. But the overall increase is the anthropogenic, and I'll come back to that later. The seasonal cycles are what I'm going to talk a little about here. So big question, is the Arctic a net source or a net sink of carbon right now? We can't actually answer that in most places, believe it or not. It's a question we've been asking for quite a while, but we're not quite there yet. Now, historically, the Arctic was a sink. That's how we end up with so much carbon locked up in those soils. And you're looking at 50% of the below ground carbon, so really high carbon content when we're looking at it. But the carbon could be released by microbial respiration if we hit some sort of tipping point. Now, the graph you can see in the picture in the top right there is what happens if you lay a fiber optic cable badly, you warm something, and then suddenly everything just takes off and it collapses down. We call that thermokarst. That exposes a lot of soil to the atmosphere. So would you get a large release of CO2 from this? We need to go measure and find out. So that's degraded ecosystems when we're looking at them. And the bottom right is what the tundra looks like when it's flooded. So it's a polygonal tundra. So you end up with pieces of the freeze-thaw cycle causes all these beautiful shapes over let's say the North Slope. This picture is from the North Slope of Alaska. So you get this beautiful shape. It makes it really difficult to walk on, but it is really pretty to look at. But what does it mean when you've got that much water underlain by permafrost? So I'm going to focus today mainly on the North Slope of Alaska, because it's one of those places that we've gotten really lucky. Lots of different groups have been measuring CO2 there for quite a while, using a technique called eddy covariance flux. So they've got towers, they measure CO2 very fast, and then they can measure whether or not there's CO2 going into the ecosystem or coming out of the ecosystem. And we have different ones. So we have some in upland tundra, which is slightly drier, and then we have some that are in the very wet coastal tundra down by the coast. And this is just a picture of Alaska and then the North Slope. So the question is the North Slope a net source or sink? It kind of depends who you talk to and what time of day you catch them, which you're going to get what kind of answers. So with the high density of measurements, if we want to scale this, any individual tower will tell us a lot about what's going on, but will it tell us about the entire region? And that's what we're going to try and focus on here. So can we scale these individual towers that see less than a kilometer around them? And it's amazing how much even 3 towers where you could see one from the other, how much variability there is. How can we scale that across the North Slope? So this is a picture of what it looks like for one of the Imnavia Creek Heath Tundra site in June of 2019, so it was before COVID when we were up there. And you can see just how much variability there is, lots of brown. This was before the big greening up for the season. So there's a lot of, everything has thawed and yet nothing is taking up carbon yet. So are the eddy flux towers representative of the region? Do our scaling methods, there's lots of different methods of scaling. Take a number, spread it out. Oh, scale it up or down. There's lots of different approaches we can take. What I'm going to talk a little about today is what if we take various things and then test whether or not they're accurate by using the atmosphere as a way to just mash it all up and then tell us where it doesn't work. So can we use airborne CO2 and methane concentrations to evaluate how we are interpreting our regional scaling for the CO2 and methane? And this is based on a lot of different aircraft data. So the NASA CARV program was in 2012 to 15, the DOE ACME program 2015, NASA Above was in 2016, NOAA had a bunch of flights in 2016, ArcticAC was 17. In any case, there's a ton of data in this window, and then there's been nothing since. So we've nothing since 2017. If I could get more data, I'd use it. So we'll use what we have for now. So what drives an atmospheric concentration? Now, if you're looking at a short-lived gas, you just say, well, whatever's in front of me with a bit of the atmosphere's here, that's my concentration. CO2 and methane, they're really long-lived. So first of all, we have to start thinking about where does it come from? So we've got these global concentrations coming in from behind, then we're going to worry about other things. So if we think about background concentrations, there's been a lot of data taken at different tower sites, and I was involved in the NASA ATOM project where we flew up and down the Pacific, up and down the Atlantic, trying to understand what's the distribution of CO2 and methane globally. So on the left here is what we got for, that would be May 2018, for CO2 up and down in altitude and going from the South Pole to the North Pole in the Pacific. So you can see that how much the CO2 is much, much higher as you go further north. Now, the highest CO2 you see there is from the Arctic. That is not emitted from the Arctic, that is being transported to the Arctic. So how much gets pushed to the far north is really important. On the right-hand side is methane, and it's an even bigger gradient in methane. And we're looking at how much of it is coming from mid-latitudes, 30, 40 degrees north, getting pushed into the Arctic. So the transport of all these longer-lived gases is very important. And we can use things like ATOM, but that was only kind of a one-off. And this is a 3D version, so if anybody's looking for more information on ATOM, Chelsea Thompson's paper in BAMS is actually a really good overview of the 300 plus things that were measured as part of ATOM. I'm not going to go into here. But if we want to use the flight data, we can look at higher altitude data that hasn't interacted with the surface. We can use towers that see the remote ocean. We can use things like ATOM to say, okay, well, this is the seasonal cycle we would expect to see of air coming into our domain. Now, this really works on the North Slope. It happens to work in Alaska. I have no idea if it would work anywhere further south because there's just so much else going on. So we're kind of lucky in where we're selecting that the backgrounds are, the variability that we see is quite low. So we've got a good handle on what our backgrounds are coming into the domain. So we take away a background CO2, and then we look at how much of an enhancement are we looking at above that. So we've got our observed CO2 enhancement. Now by that I mean there are times when the CO2 is lower than the background because it's been taken up by vegetation, or the CO2 is higher because it's been given out by the vegetation. So I mean both of those things when I say an enhancement. And then we can think about, well, how much time has the air spent interacting with these trees and grasses and ecosystems in general? If it sits in the boundary layer and you're just getting lots and lots of interaction, you'll have a huge amount of CO2 disappear into the vegetation and you will see it in the atmosphere. But it really does matter how much time it spends in the boundary layer, as well as what the concentration is. So if we want to do, if you have an eddy covariance tower, that's something where you're looking at the small scale eddies. It's the stuff that you're looking at very fast changes in CO2 and methane. And that's what we're usually looking at for like a kilometer around the tower that we're talking about. There's also a footprint that you can calculate that is the concentration footprint. So if anyone has used high split, that's an example of it. You look at where has the air come from. You're looking at it getting transported to where you are. We can use that with, in this case, it's using a polar variant of WRF. You can use how the winds are moving to calculate how much time the air has spent in the area that's influencing where you're measuring. So I'll show you some plots of what that looks like. Hopefully this has kind of gotten you towards what we're talking about here. So for something like the North Slope flights from ACME, the figure in the middle shows you where were those flights seeing the surface. So if you go high enough in altitude, you won't see the surface underneath. As you come down towards the surface, you'll see more and more influence. And we can use that calculated footprint, that surface influence, to tell us what's going on with the fluxes. So if we have a surface flux, and this is really what we want to get to, we have a surface flux of, say, CO2 uptake or emission. Can we use all of these things together? All of them feed into concentration, but if we really want to know what the flux is, we're going to have to calculate something we can start with. And in this case, Luke Schifferl, who's been working with me for a while, he's both at Harvard and Lamont, we started the conversation about how do we do the scaling of these flux towers. And Luke came up with 288 different versions of what the CO2 could be across the North Slope. Our big question then was, which one's right? Everyone does them like a multi-model thingy and they just calculate the mean and ta-da. And we're like, but we have data. We have the atmospheric data. Let's find out which one is right. Or which ones at least are no way representative of what the atmosphere sees. So he used a whole bunch of MET products. He used everything we could find, SIF products, to just calculate a simple light response curve on a very fine resolution at an hourly time scale. What should the CO2 flux be for the whole of the North Slope? Now this is using a model called VPRM. It's a very simple, take light and heat for uptake with some other things across the season, take some temperature for your respiration. It's a very simple calculation. We parameterize it using the eddy flux towers themselves. So we take the eddy flux data, so the CO2 fluxes, and then say how does it respond. But the key is not to do it for what you measure at the tower. You need to do it for what you're looking at for your gridded scaling product. And they are not the same. So if you parameterize it and come up with your various alpha, beta, whatever, they're very different because we're not necessarily trying to evaluate the gridded products, but we want to know what the response of our towers is to that kind of gridded product. So if we come across, we can look at upland coastal systems separately, looking at meteorology products, the different SIF products, different land cover maps, which ones look like anything normal. We get a huge amount of variability in that. Some of them peak early in the season, some of them late. How would we do this? So what we're going to do is, and Luke has it really nicely written up, if anybody wants to try and do this for your ecosystem, he has everything written up in biogeosciences. Pull all that together and see, well, which ones work and which don't. So, what is the flux driving the observed concentrations and which one of them works or doesn't? So this is for the aircraft data from, on the left is the ACME flights, which were June to September, so they were all of the growing season. And the bars, the vertical bars you see are the 288 different versions of the model. Now, nothing is completely out to lunch. I didn't think they would actually do as well as they do. They're on the same scale. When we started all this, a lot of stuff was not. So I thought, hey, great, we're doing great. And you can see that, so for the summertime, the July data, we see the most uptake. And towards the kind of October time period, especially in the Arctic Cat flights, which flew later, things start to go away from the one-to-one line. Now you'll see there's a huge amount of vertical variability. The 288 different models predict very different things at the shoulder seasons. So they're fairly okay when it's full summer in July. They start to diverge when we've got April data or when we're looking at something in November. Now, we can rule out some of them that really don't work. And then we can start looking at, well, we have the tower data from Barrow. Now, in Utqiagvik, so the northern end of Alaska, NOAA have been measuring CO2 for a very long time, and they measure it at all times. But the wind can come from different directions. So if we look at, in that case, the background could be wind coming off the Arctic Ocean. If we look at wind coming off the land, we can look at the enhancement of air coming off the north slope of Alaska year-round. Now, there's very little data in the summer coming from this. Various meteorology will work or won't. It works better in winter just because we have enough data to look at it. So here it's looking at, on the left-hand side, is what we're calling the unconstrained 288 different versions. They're kind of all over the place. They're high, low, but they really start to diverge when we're looking at, October, November time period. And then we can start ruling out different versions and taking which of all of these versions of it are going to make the most sense. And in this case, we've selected the Inuttaq inland tundra site, which seems to have a better representation than any of the Toolik Lake data. The CMBL coastal tundra gives us the right seasonal cycle for this. NAR meteorology, all these different things. So we've narrowed it down to the best we have seen for the different models. Now, no matter what we did, we could not get November, December, October, November, December to make any sense whatsoever. No matter what we did, there was always this, we're missing something. And we spent a very long time. What were we missing? We tried different models of what the temperature should be, permafrost models, we did all this other stuff. And we came to the conclusion that temperature alone wasn't going to answer this. We were missing something. So the atmosphere was telling us, you're missing something in the fall. Great, okay, we need an additional flux. Can we figure out what it could be? Now, Luke, if you want to play with any of these model configurations, Luke put this shiny thing together in R, and it's on the website, and you can just go play with it and see which ones work and which don't. I recommend it. But it meant that we were able to figure out, okay, well, we're missing something. We started thinking about it. We have a terrestrial model in a place that is quite wet. We have not accounted for any of that aquatic flux. Should we? What should we be including? Something else we haven't been thinking about is the process that dominates in the fall. So these ecosystems, they're active all summer long, and then it starts getting really, really cold. And it freezes from the top down, but they're also above permafrost. So it's freezing from the bottom up. And you end up with what's called the zero curtain time period, where you've got different energy and gas exchange within the soil column before everything then solidly freezes. Now, the zero curtain used to last for 2 weeks, so we didn't worry about it. It took 100 days to freeze in 2014. So everything's changing. We don't have a huge amount of data here. I'd really love some more, but it's a time period that we have been ignoring because it wasn't important, and now it is. So if we start looking at how much additional flux would we need to include if that was the representation. So it's probably coming out as pulses that we would never be able to represent. So we've calculated what we think the total amount would be, and that's the figure on the top right, and compared it to a bunch of other representations of what's going on the North Slope or around the Arctic. And many of them, my own previous papers included, completely overestimate how much CO2 is coming out in January to April. I was completely wrong. I wasn't the only one, but we were wrong. It does seem to shut down in January. So it's really the October to December time period when everything is still freezing. That's when we're missing all the fluxes. But including the inland water was really necessary to start getting this right. Now we've put a number in, represented it as best we can with our 30-meter land cover map. It's not perfect, but it does show that we need to include that. So my graduate student Luda, who has been working on a NASA Finance Fellowship, she has been looking at the YK Delta, which is the other tundra ecosystem in the Arctic. So it's in the southwest of Alaska. It's much warmer, and it's starting to be impacted a lot more. There's a lot more degraded tundra, that kind of thing. So she has a whole bunch of data working with Sue Natali at the Woodwell Climate Research Center. They have been doing NSF programs there for a long time, measuring CO2 and methane in water, which I had no experience in before Luda joined the group, and measuring to see, well, how much do you expect to see? How do we scale that for something like the YK? And the numbers we put into the North Slope stuff actually makes sense given what Luda was seeing in the field. Dumb luck, some of it, but it turns out that, well, it was quite reasonable, those numbers. So if we look at, she's looking a lot at scaling this CO2 and methane. So the first thing she was looking at was, how do we represent, what is driving the CO2 and methane in water in the YK? And now we're trying to figure out, how do we scale that? You can't scale the chemistry. So we can look at this water and say, well, it's driven by dissolved organic matter and all this pH, whatever you like. We haven't got a way to scale any of that. What we have are the physical characteristics. Is the lake really edgy? I call it edgy. There's actual technical terms for it. But how much of a perimeter do you have for the size of the lake? That has an effect on how much carbon you see in the lake. So it's the edges that really make a difference. So that's what we've been looking at now, is how much of the whole thing can you account for if you take these into account for CO2 and methane. That's not perfect, but it's a very good start in accounting for that for the aquatic systems. And she's also been looking at the eddy flux towers in the YK. Now this is Sue Natali's Moore Foundation project. They installed 2 eddy flux towers, one in a burned and one in an unburned system in the YK. And Luda's been looking, it is so heterogeneous. Normally you would just say, and there is a footprint. And you calculate a number, and that would be the end of it. And she was out there for 6 odd weeks on the tundra going, this really isn't, there's too much going on here. The fens are so different to the water bodies, which are so different to the tundra, the tussocks, that there's so much going on there. Is there a better way to represent that? So she's been really digging into, and it was completely her own project on this, but I think it's really cool, looking at how much of that heterogeneity in the footprint you see. Now the picture on the top right is just a representation of, for these eddy flux towers, you see different influences when you have wind coming from different wind directions. And they've put this tower in the middle of, and it's a complex land cover in this case, using 2-meter resolution data. What kind of ecosystems are you seeing? Now, because they've been there, they've been able to ground truth it. But things like a fen, degraded permafrost, is it wet sedge? Is it water? Is it shrub tundra? Is it lichen? I mean, I could identify maybe a fraction of it just as well. She's an ecologist that actually knows what she's doing. But how much of an influence does it make if you take that into account when you're calculating the fluxes? Because normally for a CO2 measurement of an eddy flux, you measure the net CO2 number. So you're measuring the flux of CO2, but it's driven by how much the plants take up and how much is respired at the same time. You cannot separate those out without making some assumptions. Now, one of the big issues in the Arctic is we assume that nighttime is respiration only for most eddy flux towers. It doesn't always get night in the end of June. But also we're assuming that it's completely heterogeneous. So if we ignore the landscape heterogeneity, you could be looking at about a factor of 2 difference between what you see as calculated as a net CO2 flux. So especially in this case, it's May, June, July, August, September, in case those numbers are hard to see. And in some months it doesn't make a difference, but in other months it really does. And that's just, where are we seeing? Are we seeing lots of water? Are we seeing other things? So we can leverage an awful lot more from these towers than we were just saying a number. And then what I was really surprised at is the seasonal cycle for the signals. For water, the most amount of CO2 you see coming out is in August. And I was surprised, I guess I shouldn't have been, but I kind of thought it would be earlier when it was warmer, but it's actually slightly later because of various capacities, everything else. So the greatest fen source is in July, but the greatest aquatic source is in August, September. And if you get different winds at different times, you could end up underestimating or overestimating what your CO2 uptake is. In this case, if you just assume what is used in Ameriflux, so it's kind of the standard, let's partition everything out, you'll be overestimated by nearly a factor of 2 if you take it all in. So these things will make a difference if we're trying to scale. So the data we used from Luke's study looking at the North Slope, that partitioning could have been there, but we used the raw CO2 and partitioned it with our scaling functions as it was. So there's different things we need to be careful. If you're evaluating your model, make sure it's not just being evaluated against another model. Try and get to the actual data that's driving what you're looking at. So something we're hoping to do this summer, given our luck with aircraft in the last week, who knows, but we're going to try and fly this tiny little plane. Now, I'm not getting on the plane, obviously. If we want to try and do eddy flux and find out if that's representative of everything, can we fly an aircraft to measure eddy flux across this domain? Now, this is a project led by David Sayers and Jim Anderson. They did this back in 2013, and they're looking to do it again 10 years later. And we'll try and do this out of Barrow or out of Dead Horse and figure out what we're seeing for fluxes as we look at the ecosystems, and do it slightly later than we had done before. I think it's going to be quite interesting to see. I got dragged into it as the modeler, which, if anyone knows me, will find that hilarious. But to try and help with, where do we want to target and why? What do we expect to see? What do we not expect to see? Are there certain things we need to, how are we going to do the flight planning? All this kind of stuff. So that's what I'm quite excited for that. So if anyone has any suggestions about what we should do or not on the North Slope, please let me know. I'm quite excited to talk about it. So what have we learned about Arctic CO2? We can use the atmosphere to identify which of the models is the most representative. And we've done something similar for methane. Happy to talk about it with anyone. My question with methane is, if you give me a wetland model, is it supposed to represent all the biospheric methane fluxes? Because they don't. It's a long story. We can try and have more of a discussion on that. But North Slope tundra, it's not a consistent source of sink of CO2 right now. It depends on how good was your summer for taking up the CO2. It's completely driven by what is the summer doing. Now, how much we account for the winter decides whether or not we're either side of that line too. So making sure that we're actually accounting for what the contributions are is really important. And the atmosphere integrates whatever you give it, so terrestrial, aquatic. We have to make sure that we're taking all of that into account. And then, if we're looking at fluxes from inland water and additional emissions during the soil freeze-up, that's what we can use to explain some of the longer-term data. That and the homogeneous footprints, we need to be very careful in how we're doing that. Okay, so that was kind of CO2. Something I've been quite concerned about is what is going on with methane in the atmosphere. So methane has been measured for slightly less long than CO2. And globally, we were looking at, just before the pandemic, we were looking at 2 or 3 in the 2010s, and then 7 ppb in like 2019. Slightly concerning. And then 2020, 21, and 22, it went off the rails. We're looking at 20-odd ppb increase in methane. And the atmospheric chemistry community has no idea why. And I'm slightly embarrassed to say that. There are full-blown arguments. I can't even tell you, is it a change in the source or a change in the sinks? We got nothing. We got some information. It has to be something long-lived enough to last for 3 years in a row, so that has taken a whole bunch of stuff off the plate. But if anybody wants to talk about that over beers, please let me know. We can rant about it. But it's embarrassing that we can't tell you why it's increasing like this. What do we not know about methane that means we can't tell you why it's going up so much? Now, we've got this record growth, it's a sparse network, we need to do more about it. If you look at methane, you'll notice that there's not just the growth, there's also a seasonal cycle on there. And something that I've been quite interested in since I got to New York is why. But there's been all this like, oh, scientists, unexplained, blah, blah, blah. We still have no idea. We're still trying to figure it out. I would recommend any students that are interested in digging into it, please go for it. But make sure you put a time limit on how much time you're going to spend on it. I don't think we have enough data to tell you the answer. So I'm all for more measurements of everything. Now, if we want to look at where CO2 is coming from, we looked at that picture globally. We were looking at massive amounts of CO2 moving towards the Arctic. Where is it coming from? 70% of the global CO2 comes from urban areas. I was looking at trying to figure out what are we looking at for CO2. And then I saw this study where looking at the footprints of CO2 emission per city versus the number of people in the city. And the US has quite a few cities on this list. I happened to move to the one that's top of the list. So I moved to New York, 2018, and you're suddenly looking at the largest regional source of CO2 in the whole of the US. So if we're looking at this, what does this mean? What are we going to do? So I started digging into carbon emissions. I also started measuring stuff because that's what I do, and I wanted to know, unfortunately wanted to know what I was breathing. Probably would have been better off not knowing, but now I do. We'll try and do something about it. So carbon emissions from New York City. The city have been quite committed to trying to understand where their carbon emissions are coming from. So this New York City government came up with this estimate of where the carbon emissions are from. Things like natural gas. I didn't realize, so I'm Irish, if you can't tell from the accent, we don't do things like New York do. In fact, I don't think anyone does things like New York do. They finally got rid of bunker fuel as a home heating source in 2015. It's been banned in Europe since the 60s. Like, there are so many things wrong with New York, and you think it's so progressive, and they just forgot to change the rules. And so assume nothing about New York is what I've learned in the last couple of years. But they have this inventory. Would we know if something was missing from the inventory? Would we know if something was incorrect in the inventory? And if we want to know that, how do we go about doing that? Can we measure CO2 and methane in the city and try and understand what we're missing or not? So the city has an estimate of 0.7% of all natural gas used in the city is what they call fugitive emissions, so accounting for leaks on the street or not using it properly or whatever. So that's their estimate for that one. I'm going to say that that's a load of rubbish. But let me point out a little of why. We'll start with the CO2 stuff first. So, now, something I'm quite interested in, the reason I'm actually interested in this, CO2 doesn't hurt any of us unless you get to the point of like nearly poisoning yourself. Like, it doesn't do anything to humans, neither does methane. However, the stuff that's emitted with CO2 when you burn it in a city kills millions of people every year. It is the number 2 or something globally of killing people. So when you burn a fossil fuel, if it's natural gas, you've got methane and ethane. If you burn it, it produces NOx. If you don't burn it properly, it produces carbon monoxide, CO. If you've got trash, if you've got landfills, you've got a whole bunch of sulfur species that go with it, the smell of the landfill, and a whole bunch of other things, but there's no ethane. So those differences mean that we can start to use all these different gas species as a way to figure out what sectors are contributing to the total number we see. So if we see methane on a street, are we seeing methane from natural gas or from the sewers? Methane gets produced in sewers. So something we've been talking a lot about is trying to understand what the different emitted species are, and can we make sure to not make things worse as we try to improve the climate. So Europe in the 90s adopted the policy of diesel is better than petrol because you can travel further on a gallon of diesel. It has killed over 32,000 people in the last few years because the NOx emissions from diesel they just didn't really, they didn't have any atmospheric chemist in the room to tell them how bad an idea that was. And it was just, for climate, we're going to do this. The fact that their air quality is now so much worse than the US barely comes up now and again. Now, there was the whole VW, Volkswagen lied about how much they were emitting, but I had friends who were measuring NOx in London and knew it was going on for years and nobody would listen. They took the EPA to actually nail someone down. So, if we want to try and improve this, we need to do it in a way that doesn't harm anyone. We need more information to be able to figure out what those things would be. So, same principle as we used in the Arctic. So we're going to do, using the atmosphere to estimate total CO2 methane. There's been a fair few aircraft campaigns around the area over the past fair few years. But most of them are snapshots. So they fly by, they get maybe a day or two, and then they're gone. So what I'm quite interested in is A, the seasonal cycle of a lot of this, but B, these top-down snapshots, they're all saying that there's way more methane than should be there given what we know about our estimates from our inventories. So we take our inventories, we look at it compared to the atmosphere, stuff isn't making sense. Now, the CO2 is not too bad. Now, it's massive, but it's not exactly right, and I'm going to come back to that in a second, but for methane and CO, it's just way off. Now, this is New York City. The darker the red, the more concrete there is. This is a very heavy concrete area. So it's impervious surface area. And you can see that there's kind of Manhattan's in the middle. You can see Central Park is the strip down the middle of Manhattan. There's an island to the bottom left, that's Staten Island. It had the world's largest landfill when it closed in 2000. They finally capped it in November of 2021. Took them 20 years, it was a big landfill. So there's a lot of different things in this area. You'll notice that there's 3 green dots in the bottom left. That's the air quality measurement sites from the state of New Jersey. They are surrounding the largest refinery in the Northeast, alongside the port of New York and New Jersey, which I think is only second to, I don't know, Long Beach or something massive. And then the New York State have the other ones up the top, and these are just where they're measuring CO, and we've been looking at evaluating that. So we've been trying to build up a network of CO2, methane, and then adding CO concentrations to that. And that's working with Lee Murray, who's at the University of Rochester, who had started doing a lot of stuff upstate, and then I moved to New York, and we said we'd try and do something in the city. And then there's also a NIST-operated Earth Network site, which there's another site here at this campus, which is really cool to see. And that's looking at it in Mineola, where there's going to be a nice big aircraft, there's going to be aircraft tied in, but a ground-based campaign this summer. So we're going to add a lot more measurements to that little pink dot on the far right. So I've been measuring various things on a really tall building in Harlem since about 2019, but only seasonally. So I've been doing this on the side between funded projects. So we've been trying to get the spring for each year. So we have a really nice pitch. The building is up on a hill. We can see all the way downtown. So the bottom left, that's Midtown Manhattan with a whole bunch of residential before you get to the park. The left side, you can actually see down the LaGuardia runway. It's pretty cool. And the top right is the quantum cascade laser system, so we can get methane, ethane, N2O, CO, CO2, and all of those can tell us different things about the methane, CO2 budgets. And then using the Picaro more frequently, so we kind of leave that running, and that's now running year round. One of the things we do have in one particular wind direction is the natural gas distribution hub is right beside the wastewater treatment plant. So 2 potential methane sources, but with different other characteristics that we need to take care of. So that's quite common in New York. You're looking at one source right beside another, you have to try and figure out what you're actually looking at. So if we think about where the air is coming in from, we can use some of these different background locations. So for CO, we'll have some places methane, CO2, and for the kind of right bottom orange one, we've only just set up the measurement site there, so that started in January, and we're going to keep going year round in New Brunswick. So Dan Wei is a postdoc working in my group, and she has been, something we were kind of interested in was, okay, well, we have all these emissions of CO2, but when I got there, I realized New York is actually kind of green. There's over 1 million trees in New York City. It's got a 22% canopy cover. I had no idea. I thought New York was, Midtown Manhattan, where there's nothing but skyscrapers. So we started looking into it, and the two graphs here are from different models of northeast biogenic CO2 fluxes. And both of them pretty much say that there are no trees in New York, so the number should be tiny. And I was like, that doesn't seem to make sense. Now, the one on the left is a 12 kilometer. And because it's a 12 kilometer map, they're saying that there's no trees, fair enough. The other one is, I think, 2 kilometer, Sharon's paper looking at various areas there. So if we're seeing trees there, is there a better way to represent this? So Dan went and found it using NLCD, so the 30-meter resolution map. Look and see what do we see in New York City. And you can see on the left, the dark purple is the high intensity buildings. And then medium, low, and then there's a whole bunch of open space. There's actually quite a lot of green on that for where I was surprised at how green some of it could be. And on the right-hand side then is New York City has a 6-inch, 15-centimeter LiDAR map of land cover in New York City. Doesn't extend into New Jersey, but it gives us a huge amount of information about New York City. And what you'll notice is there are street trees, what I knew as street trees, where you've lots of trees down along the street, but you also have a huge amount of greenery in the backyards in the middle of the blocks. And that's what I was really surprised at. There are so many trees hidden away from view that you can see when you're looking down from our building. There's a whole bunch of greenery. So what kind of carbon uptake are we seeing with that, or respiration, as we go along? So we started thinking about how would we represent this. So on the right-hand side in the yellow is, if we assume everything with the high intensity doesn't have any trees, we get the yellow, which is pretty much there is no CO2 flux. If we look at all of the greenery and say, oh, it's a forest, we get the middle one. And if we assume it's a grassland, we start getting the one on the left. So there's actually quite a big difference between what carbon uptake we would predict if we're looking at a forest and a grassland. Now, this is a modeling study. We've started doing the field work to figure out, well, which one's real, which one's the most representative. We're doing a lot of boots on the ground type stuff last summer, this summer. It'll be lots of fun, but there's a lot of work to do to nail down which exactly is this. But if we want to assume we've got these two different versions, is it grass or is it tree? Can we use the atmosphere to tell us if either of them is anywhere right? Does it make any sense whatsoever? So we started using the Edgar CO2 emissions, which, who knows, they might or they might not work. And look at the difference between the Stockholm, New Jersey, and Mineola data. So the Anna-Karin's tall tower data, use the difference between those and see if we can understand how much CO2 enhancement can we explain in the New York area. So I was really surprised that that one-to-one line was even on the graph, if I'm perfectly honest. It means that we're looking at Edgar CO2 and our biospheric fluxes kind of makes sense. Now there's huge error bars, and something we have to do over the next few years is figure out how to really reduce those error bars. But they're on the same plot. I did not expect them to be. I honestly thought they were going to be way out to lunch, and that dashed line is the one-to-one. So what does that tell us about the system? So we're looking at 20 to 40% of the Edgar emissions can be scooped up by the biosphere in the afternoon in July. Now this is just a typical, we took a 1 day, I think it's a couple of days average. But what you'll notice here, so the figure on the right is a time series by sector of what the CO2 looks like in the atmosphere, taking our footprints that we've calculated the same way we do in the Arctic, with the Edgar CO2 inventory, and then moved it through the atmosphere to our tower. Now, what you can see is the power industry, combustion, and energy for buildings absolutely and utterly swamp everything else. Traffic is a tiny little orange line that's kind of hidden down the middle. So when people talk about massive traffic in New York, that is the least of our worries. It's big by any other standards, but it is not big here. And yet, if we assume that we have grassland or trees, by the afternoon, the trees take up all the CO2 from the cars. That's wonderful news, but it means we have a long way to go, given that the traffic is such a small fraction of the total CO2 emissions, anthropogenic emissions that we're looking at. So there's a big interest in doubling the number of trees in New York City, or at least, 30% canopy cover. Let's increase the number of trees. Trees are fantastic for minimizing urban heat island effects. They take up carbon. It's going to be awesome. The only problem is we started looking at, we have all these trees, we have the species, let's run Megan, sorry Alex, and see what we get. If they add 1 million more oak trees, we are such in trouble. Okay, let me explain slightly. If certain species of trees are going to emit volatile organic compounds, so isoprene in particular is what I'm interested in, most places, doesn't matter. You'd just be a lovely smell. New York City is NOx saturated. There's so much traffic in New York that the amount of NOx is one of the few cities left in the US where the NOx dominates. So you've got so much NOx in the atmosphere. If you increase or decrease your VOCs by even a tiny amount, you make a plume of ozone that hits Connecticut and can be seen all the way up in Maine at Acadia National Park. So if we get this wrong, it could have huge implications downwind. Connecticut already disliked New York, but we just blame New Jersey. So it's kind of a running theme, you blame whoever's down upwind. So we ran this. On the left side is what you're looking at for isoprene emissions or emission rates for what you would see in running it through the EIS system, Megan with CMAC and smoke and everything else. This is what they think the isoprene would be, which is nothing in the city. On the right-hand side is using our 30-meter maps for the CO2 to understand a bit about, well, where are the trees? Where are these little parks? We have parks that are the size of city blocks that are full of oak trees. How much does that influence how much is going on there? If they're going to double all these, we could be in real trouble. So we need to know more about what is going on where, and that's our aim for this summer. And that's why I'm talking about that will get us out of it. A lot of information on that, but so we're learning a lot about what kind of tree is where really does matter for the systems that we're looking for. Because oaks are native to the Northeast. They survive really well in high pollution. They do really well in really hot conditions. They're like the ideal tree, except for the isoprene. So we need to have that conversation and make sure that the atmospheric chemists are in the room with the urban planners. So I started measuring just before COVID hit. And I learned what it means to turn off a city. Like literally you could walk down the middle of the road, there was no one there. It was kind of freaky. So there was all of this, oh my God, we've all these changes. And yes, we pretty much, the cars disappeared off the road. We were looking at 80% drop in transit, 60% drop in traffic. I walked up through Times Square. It was the freakiest 28 days later thing I've ever seen. You know, it was a very big change for New York. So we were measuring on the roof and we started looking at it and we did see some changes. My big problem was, were they normal changes? Were they regular seasonal changes? Were they more than, you know, did we just get really lucky with the weather? Turns out we got really lucky with the weather, but that wasn't the only thing happening. So looking at the changes, so the top one is CO2, and we had a pretty big drop in the CO2, 10 ppm. We had a really big drop, I thought, in the methane. I was like, wow, this really is dropping a lot in the afternoons. And a 200 ppb drop in CO. Now, you guys have what, 200 here in the background? New York kind of starts at 500 and goes from there, so there's an awful lot of CO in the atmosphere there. But what you'll notice is for the CO2 in May, so the gray is January, February, the red is late March and April, the May is when the growing season has started to kick in, and we can see just how much the afternoon kind of drops from the others. But what does this mean? My big question was, we could write a paper on this right now, say there's a massive drop, get something that will be worth nothing to anyone because we haven't actually thought about what has happened in meteorology, does this happen every year, what's going on here? And I was so glad I did not write that paper because it turns out April and May are when you have the biggest decrease in usage of natural gas in New York City every year. So we got lucky with the emissions, would have been dropping anyway. So while there was a big drop, most people needed to heat their homes and then not. Even if they left, buildings in New York are run by one big boiler in the basement. If there's one person left in the building, the heat has to be on. So there was very little change in all of that. So this is data from the City University of New York, and what you'll notice is that April, May are the minimum natural gas usage in the entire year. Now, if you think back to all those aircraft projects, they aim for April and May because it's the best weather and before the biosphere comes out. So it's the best time you're going to get your flight data for New York City. So even though they've been saying it's a factor of 3 and 4 that we need to increase the inventory, that's kind of the minimum of what it would be. So I'm waiting to see if we can get them back at different times of seasons. Now, New York is where they use natural gas for both the heating in the winter and the AC cooling in the summer. So there's a lot of natural gas use. There's more in the winter, but it's not zero in the summer, not by a long shot. So something we've been digging into is how do we measure a lot of these things properly? So we started testing a bunch of instruments. So we have the QCL from Aeroline, we got a Picaro for ethane, please don't buy one if you're considering it. And then we got an Aeris, which is one of these little you can pick it up and walk away. Now the QCL, if I'm in a good mood, I can carry it with someone else from here to here, and that's about it. It is so heavy, it takes forever. The Aeris, I pick it up, I can practically throw it in the air. Now, what we were finding is that there's a lot of these short-lived, very large methane-ethane plumes. We've been seeing it with the QCL for a long time. But we were trying to figure out, what would be driving a lot of this? And if we look at the other gas species, so we see the methane. I was expecting to see a whole bunch of wastewater treatment plant emissions, which we do when we're driving around. But at this site, what we're really seeing is very high methane, and it's really well correlated with ethane, so it's natural gas, but it's really well correlated with CO, and there should be an awful lot more CO2 if we look at the combustion efficiency, and it's not there. So we're looking at somebody really badly burning natural gas and contributing all that natural gas to the atmosphere. Now we see different plumes from different wind directions. This is just one day where we saw different things moving through. But the ratio isn't what I thought it should be. So we went back and checked. The ethane to methane ratio was about 3%. At the rooftop, we're measuring, closer to 1. So where is all that ethane gone? And we've been assuming that the methane-ethane ratio is our way of tracking all this thermogenic methane. What if that's wrong? So we're trying to write it up at the moment and figure out what's going on. If anyone has any suggestions, please let me know. And the other really surprising thing, now I flew around the world measuring N2O. We fought over a PPB being this massive change. And then we put the instrument on the roof and went, oh. And I went looking for hospitals and dentists, bakeries, breweries, kids getting high. I went through the gambit of what could possibly be going on here. In this wind direction, we have a wastewater treatment plant 3 miles away. And we're seeing 100 ppb enhancements. So we put it in a van, drove it around. SUNY Albany helped us do a whole bunch of sampling around New York. This got to a ppm of N2O outside the gates of the wastewater treatment plant. I think they had an issue. So something I had not figured in was N2O in cities being a really big source of greenhouse gases, and yet there we are. So sometimes measuring some things, you can get some interesting results regardless. So we need to figure out why that one particular wastewater treatment plant does so much, when the other one in the other wind direction does not. So it's not every wastewater treatment plant either. Okay, so what have we learned about New York? We need to include the biogenic CO2 to actually constrain cities. Even if a tree matters in New York, it's going to matter everywhere because there's so much concrete it has to. The co-emitted species. If you measure a bunch of stuff, you can actually learn about what's driving the net signal you're seeing. You want to know where your methane's coming from? Measure ethane, measure CO. Find out what else is going on. Incomplete combustion is way more of an issue than I thought. And we don't see that on streets when we're driving around. We see it on the rooftop when we're measuring at chimney level. And fair enough, we're measuring at chimney level. Maybe that's something we need to worry about. Boston have been fixing pipes for the last how many years, and yet the network there is not seeing a change in the methane in the atmosphere. Is it because we're focusing on fixing the wrong things? Good question. Now, if we can mitigate the greenhouse gases, if we can focus on the combustion and reducing that, we can improve air quality. I think that's a win. We need to be careful and make sure we're monitoring everything, that nothing else happens that we haven't expected, but it's one way to think about it. So thank you for your time. My group is awesome, and some of the former, we had a whole bunch of interns last summer, and one of my former interns is here. And they've been great for making sure that all the field work we're doing actually works well. And lots of people deserve thank yous. So thank you very much for your time.
So how often do you actually find yourself in a room with policymakers so that you can pass on this wisdom to people making decisions?
More than I expected 3 years ago. So we got funding from New York State, NYSERDA, who you see up there. So the network we're putting together is funded by New York State. And as part of that process, they have these meetings with an advisory council. And when I started all this, that meant 5 people in a room in Albany, and you went up and you said hello and you showed them what you were doing, and that was fine. And then the more recent stuff is now online, and 100 people turn up, and the number of emails coming in is immense. So we have to be right, because they are developing New York State's methane mitigation based on what we're finding. And it's been a bit of pressure, but it means that what we're saying is actually making a difference. So they know about the combustion stuff, we need to finish writing it up and figure out what's going on. And Con Ed, so the local gas utility, are part of that committee. And I have a number, if we find a leak, they expect a phone call. They don't want any leaks in Manhattan. They have been surprisingly good about it. And I think that's why we're not seeing the street emissions that previous studies saw in 2014, 2015. Studies driving around saw huge methane on the streets. It's not there anymore. There are some, but you bring it up and they have it fixed within a week, not even. So more recently, yes, yeah, surprisingly. Because it's not really my forte. I'm a science person, so I have to be kind of figure out how to explain things. But it's been good to do. It's a good exercise. I feel like we're making a difference.
So for the first study, you show numbers is a very good talk.
Thanks.
So for the first study, you show when you estimate GDP, you use your model, and there's T response, we can see the T response like this. So are you using the same country response for all the medications? I think it's supposed to be different for different medications, because kind of Arctic also this sensitivity to temperature change. Also, what kind of temperature you use is air temperature, or it's kind of temperature?
So it's air temperature in all of them. So the approach we took, we looked at the individual towers and the temperature they were measuring and looked at that response first. And then what we were trying to do was figure out how do we then scale that. So we used the air temperature, 2-meter air temperature from NAR, from ERA, and all the meteorological gridded products. Now they are slightly different. So it's something like Tulik. If you look at the temperature at the towers, you can actually, I think it's either a pressure gradient or a temperature gradient down the hill that we can't capture because the grid box covers all 3 of those flux towers. So the approach we took is it's going to introduce some uncertainty. We would see something in there, but we just moved forward with just using the grid box for that. But there is definitely slight temperature differences in there. Now we've also taken the approach of with the 30-meter grid box. You know, we're looking at 25-kilometer meteorology, so that means it's got everything in all of this. So the different scales, it'd be wonderful to get a higher resolution meteorological products to be able to do more with that. But also what Luda is finding with how important it is to have the heterogeneity there, we don't have that in the whole North Slope study. And it's something that I think we're going to have to rethink a little. How would we go about incorporating some of those results into it? You know, if we're looking at more degraded permafrost, or you're looking at a lot more of that in certain areas, do we need to account for that more? So this is very much a first cut at what we can do, but yes, I think it's really important. We're going to have to figure out how to get more of that heterogeneity kind of into everything we're seeing. So, yeah, go ahead.
I have another question about the second project, about the city methane measurements. So all the methane still is all these still active. I mean, not that's active, but still the same as methane is orange activities.
And soil uptake.
Yes. Oh.
Yeah.
So, but things for the city region, they're always besides isoprene, getting some CCR, also NOx, but also consumer products.
Mm-hmm.
How do you consider these in environments or modeling to
So we haven't, but Drew Gentner and John Mack have. So they were at the same time, they had a PTRMS, a high-res top, on the roof measuring for some of during COVID, just don't look. And they're finding that there was a big change. So things like D5-siloxane really changed when people just got off the streets. Whereas other things, the following year, we much more isoprene early on, as temperatures were much warmer in 2021 than they were in 2020, ice cream went very high. And it's been very interesting to see the differences in some of those species. So yeah, there's a lot going on there. But something we haven't been doing is incorporating enough variability in the methane and CO into things like reactivity calculations. So we've included the CO for song stuff, but we don't really think about methane. But if we're looking at 10 ppm of methane, that has to have an effect on something. Like, is it affecting formaldehyde production? And then, so I don't know, but I think it's something we need a lot more data on in order to be able to tell if it's something we do need to be taking into, like, the chemistry discussion. Because most people look at methane and go, it's not reactive at the time. At these concentrations, we might have to start thinking about it.
It's a really interesting city dynamics. The nitrous, I was curious about the nitrous oxide. That really surprised me how much utility got. So that must mean, like, I think those treatment plants have to oxygenate their sewage before they can pump it, like, offshore or get rid of it. So to make that much into it, they must be not oxygenating it very well. Are you able to, is it easy to measure N2O? It used to be really hard to measure N2O, but could you go in there and work with them to see if their oxygen levels are changing and that's what's contributing to this?
So one hiccup is that the city are terrified of me because I'm funded by the state, and they don't talk to one another. So we told them what we were seeing outside on the street, and we're like, if we're seeing a ppm, they must be seeing 25 ppm, which is toxic, inside the plant somewhere. Now, it turns out that particular plant takes the solids from the other plant nearby, the other wind direction, and they put it into a ship, bring it around, and process it all at Ward Island, which nobody lives on that island. So it's the least likely to impact anyone, whereas the one to the west of us is a park right in a residential area, and the park is on top of the wastewater treatment plant. So I think they bring a lot of the solids for the nitrogen treatment part of it over to Ward Island. So I think it's worse than it would be otherwise. But yeah, I think I'm gonna have to pull rank and see if they'll let me in, but they really don't want the state telling them what to do. So I work with colleagues in City University of New York and give them instruments to go in and snoop around. So I just got an N2O CO from Eris, which is one of these small ones, because the QCL is not portable. This thing is portable. So I'm gonna see if we can sneak it in there somewhere and see what is actually going on, because it doesn't make any sense. But Mark Zondo from Princeton has been driving around with an open path N2O, and he's been doing N2O and ammonia. And he's also been seeing massive numbers from this particular plant. So I don't think it was a one-off the day we drove by, and I think the long-term time series show that it's sporadic. So not every time the wind direction comes over, but when it does, it's huge. So, yeah.
So yeah, let's thank Roisin again for this wonderful talk. And she's going to